Hello, I'm Callahan. I will be presenting our work on the upgrade of RIT factory management software from MESA to Siemens OpCenter Semiconductor. During this talk, I will be covering why we teach microelectronic manufacturing at RIT, our current manufacturing software, the Manufacturing Execution System application, or MESA, our path to improving our manufacturing software capabilities, our solution of upgrading Siemens OpCenter Semiconductor, and finally, the future implementation possibilities that this software presents to us. To begin, I'm going to give an overview of the manufacturing education in the microelectronic engineering program. While the microelectronic engineering program teaches a variety of subjects in our field, one of the topics that can really only be taught at RIT to undergrads due to our fab is manufacturing. Manufacturing education is incredibly useful when trying to get a job or co-op, and many years ago, the program had to find the best way to teach it. This eventually culminated in the CMOS factory class, where students were able to split into groups and work to take multiple CMOS lots through our in-house fab. This experience is facilitated by the factory management software MESA. So, if we want to teach manufacturing, why do we need to have factory management software? Manufacturing software is an industry standard. Any wafer fab that processes lots will either have a proprietary or in-house lot or product management system. The manufacturing software allows for the tracking of a lot through a process and helps with the standardization of processes between many users. The tracking of lots and data attached to them, whether it's from a tool measures or in-process device testing, allows for product parameters to be monitored by SPC charts. SPC monitoring is crucial to manufacturing a consistent working product and being able to diagnose process variation. A standardized process is a requisite for any sort of statistical process control, and manufacturing software helps facilitate that. The exposure to a proper manufacturing software also serves as a vital education tool for the students in the program, as no other university offers this level of exposure and experience to its undergrads. This unique exposure to the software and its methodology provides a unique leg up for students when they are searching for a co-op or full-time job. Despite everything I mentioned on the previous slide, our current manufacturing software, MESA, is over 30 years old and at this point has multiple network security, hardware reliability, and interface issues. Our manufacturing software needed an upgrade, and if we wanted to continue to provide a modern manufacturing education to micro students and all the benefits that come with that. So, let's talk more in depth about our current manufacturing solution, the Manufacturing Execution System application, or MESA. MESA was acquired by the program in the 1990s via a grant from IBM, so the students could become familiar with, and at the time, industry standard factory management software. But what exactly is MESA and what does it do? MESA is a database display software, meaning that everything on screen is simply a visual representation of a database table, and every operation conducted in it simply modifies the data in certain tables. These tables and operations are used to manage various parts of the manufacturing process, such as lot moving, data entry, process instructions, and transaction monitoring. Here is a brief look at the internal operation of MESA, with a figure on the left showing the operator landing screen and the figure on the right showing the process step page for the CMOS 150 product. As you can see, MESA uses a DOS-like interface for user interaction. That means only keystrokes and text entry are accepted inputs. Clicking to move around is not possible. Instead, function keys, F1 through F24, are used to manipulate your location and execute other basic page functions. MESA, in its current state, has multiple issues that make its continued use non-ideal. First and most importantly, the database is solely run and stored on the AS400 in the clean room. Not only does the use of an antiquated computer present security issues, but, as IT does not want to continue to maintain it, if the computer goes down, we lose MESA and all of its associated data. In addition to this, using MESA as a user is clunky at best. The terminal DOS-based navigation does not match with the current program standards. Querying data is also exceedingly difficult due to an old naming conventions necessitated by old database design rules. Software is no longer as universally reachable in the fab and was originally designed to be. An SPC chart-making software that could read from MESA is also no longer functioning. Because of all this, MESA in its current state is only useful for the micro CMOS factory class. With all these issues with MESA and the desire to further manufacturing education in microelectronics program, how do we proceed? Looking forward towards restoring the functionality for factory management software, there are 4 paths we could go down. Path 1 would be to restore the lost functionality of MESA and continue using it. such as with the old SPC software. This would prove difficult as interacting with MESA and the AS400 is rather complicated, and we'd want to phase up the AS400 anyways. Path 2 would be to keep MESA in its current state and simply work on producing new SPC software that can be read in from MESA. While much simpler and more reasonable than option 1, this once again would prove to be a short-term fix to a long-term problem. Path 3 would be to create our own simplistic MESA equivalent software. This would provide only functionality to run the CMOS 150 flow for our factory class. It would be self-supported, long-term solution that could be expanded upon in the future. Path 4 was to upgrade from MESA to a new proprietary software. This was the best theoretical solution, as it would modernize RIT student factory. However, this implementation of these kinds of modern software can be incredibly complex, and RIT have been hesitant in the past to provide resources for this effort. From the start of this project, we initially settled upon writing our own factory management software. This would allow us the most control over every aspect of the software, but hand in hand with this, we would be completely responsible if any issue arose. We quickly realized that something of this scale would likely require a cross-disciplinary project with software engineering, or at the very least require software advising from the department. Starting out in a rather ambitious state, the complexity and sheer scale of a full management software was causing us to limit our scope and functionality. This led to multiple proposals and reworks being put through and discussed for most of the fall. The entire time we had in the back of our minds that the new best option was to somehow require the Siemens OpCenter Semiconductor software suite. Siemens had bought Camstar years ago, so the OpCenter software was actually a direct descendant and upgrade version of MESA. The question would be if Siemens responded to us if we asked again, and even if they did, would RIT give us the requisite resources to go through the install, even if we acquired the software. With our self-coded project being worked on still, we decided to reach out to Siemens and see how much it would cost us to buy OpCenter for educational purposes off of them. But because of our years of using MESA in education, Siemens generously offered to upgrade our manufacturing software to OpCenter for free, so we could continue to provide manufacturing education to future students. This unexpected change put the project temporarily on hold, as now we would actually be able to modernize the student fab for current factory management software. What we did not anticipate was the fact that it would take through February to get the software fully working on RIT's internal network. Now that we have Siemens OpCenter Semiconductor, how does it work, and how is the PMOS process integrated into it? As opposed to the table-based design of MESA, OpCenter is an object-based program. Using constructors and templates, each layer of a system is defined and then can be related back to one another. The highest level objects takes properties and defined rules from lower level objects. This allows for an immense amount of specification if desired during certain steps. When you are defining a new product, for example, a new PMOS or CMOS flow, you define the process from the bottom up and the software reads it from the top down. If you define more and more objects unique to your factory, the setup of future projects becomes easier and you can inherit objects between products. Here's a quick look comparing the landing page that a student would find themselves in after logging in as an operator. On the left, you see old MESA DOS interface. You need to use number and function keys to navigate through these tables and only have access to one of the screens at once. On the right is the new OpCenter Semiconductor web interface. This interface can be accessed on any computer that is connected to the RIT network and it fully integrates modern design practices. Simply put, you could click on things. You can easily select between active lots, view instructions for those lots, move individual wafers instead of full lots, and query usage data from all from this screen. As a starting point and learning tool, we decided to implement the PMOS process used in the IC Tech class into OpCenter. This was done because our PMOS process is our simplest process that produces full working transistors and is still used today. In order to build this, an overall understanding of how the process is defined was needed to be first established. We needed to define what various specs used throughout the PMOS process and what instructions desired data collection was needed at each step. In addition to this, 2 accounts or view types would need to be created, admin and student. Both accounts use an RIT login and are authenticated over Shibboleth. The admin account allows for the creation and modification of all aspects of the process as well as user creation. The user or student account allows for access to lot movement, instructional information, and data entry. The first step in the creation of the PMOS process was to pull all the instructions from MESA into a design document. This pre-work allowed me to both get ready for the process flow correctly into OpCenter and have something to do while waiting for the install of OpCenter to be finished. After a few failed attempts at importing the process into OpCenter, we learned about the Excel loaders that have been included with the software. Excel loaders are Excel pages that have SQL queries integrated into them. This allows for information that you put onto a worksheet to be sent out to and interpreted by an outside software, in this case, Siemens OpCenter Semiconductor. The only things that were defined at this point in OpCenter were the step names, what spec was assigned to that step, and the flow between the steps. After the flow had been fully implemented, the most complex part of the learning curve began. How to fully define a spec so the user sees all that they need to when they enter a step in that process. Well, there are multiple ways to do this, some much easier than others. We opted to use task lists, data points, and electronic procedures. Each step in a process is assigned to a spec. For example, the mask level 1 lithography step is assigned to the spec called PH03. The instructions for a step were then designated on a task list. These task lists are HTML formatted and therefore support a wide range of options, including having images placed in them. These instructions can also have mandatory or optional data points assigned to them. These data points can use any of the common variable types such as int or string, and have limits assigned to them. An important note here is that the limits can actually be displayed if a user is defined. So if you have limits, you can show them on either side of that data point. In order to help facilitate the future use of this software, I also created a video tutorial so that people in the future admirals will have a much easier time getting set up than we did. The tutorials I created were user creation, full spec definition creation, and the process configuration in order to start a new or existing product. Now that we have established how to use OpCenter to make a product flow, let's go over to some possible additional implementations for future use. The first and most crucial future goal is to get the CMOS process flow implemented into OpCenter. Once this is complete, we can then use OpCenter and set up MESA to run the CMOS factory class. Once this is fully implemented, OpCenter can be opened up to other microwave classes that have designated process flows so that they can be standardized and get statistical data for their work. There is also the opportunity for research groups to begin using the software for standardization and data collection. However, a more robust listing of this SFML toolset, equipment, and procedures will be needed to be implemented before this will be possible. OpCenter is an incredibly powerful program and is designed to be able to control and standardize everything across an entire production factory. This means that we have many different areas that we could expand into being controlled by OpCenter. For example, we could replace the tool reservation system of OpCenter. OpCenter allows for each bay and tool to be individually identified and controlled from itself. While most of our tools are too old to be properly integrated with modern software, tool reservation would be possible. The largest and most difficult issue to overcome here is that every single process would need to be put into OpCenter in order for a tool to be checked out under it, and which would be an immense undertaking. In addition to this, the idea of a product in OpCenter is very generic and can apply to anything the fab used during a process flow. While wafers are already tracked as products as they go into the PMOS flow, all chemicals and consumable usage could also be tracked in OpCenter, allowing for the advanced inventory tracking system to be implemented. This is the same fault as the tool management scenario, though, as every process may need to be put into OpCenter before this works. In conclusion, MESA, a vital manufacturing teaching tool to ready students for industry, has now been upgraded to fit modern software and network accessibility standards. We have also implemented our most basic process flow into the new OpCenter software, and will be testing out how to use a real case during the summer. Future implementation of the CMOS 150 process flow will be done in the fall semester with the hopes of running the CMOS factory class of OpCenter instead of MESA. As faculty, students, researchers, and staff become familiarized with the full capabilities of Siemens OpCenter Semiconductor software suite, it is anticipated that a push towards a more robust adoption of this feature will occur. I want to say thank you to Dr. Robert Pearson for being my advisor and helping me coordinate with Siemens, Dr. Lynn Fuller for the documentation and his work on the original MESA, Jim Stefano for his unyielding patience with us during the installation and dealing with our constant troubleshooting issues, Jeff Morris and Jeff Kalsbor, who were employees of Siemens OpCenter and for helping us troubleshooting and providing some tutorials for us, and Paul, Dave, Carl, Emmanuel, and Nikhail for keeping me sane over these last 5 years. Some references. And thank you.